So we have to wait for more people, isn't it?
Okay, good morning, good afternoon, and welcome to Biomass Canada Cluster webinar series. I'm not sure if you have attended the previous webinars. The focus of this webinar series is on project updates. So the primary investigator for different activity we have in Biomass Canada Cluster, they will provide updates on the projects. So far, we had 4 webinars, and in each webinar, we had 2 project leaders that are provided update on 8 projects. And today is actually the last webinar from this series, and we have Dr. Ajay Dalai from University of Saskatchewan. He's going to provide update on 2 activities he's been leading. And in case if you have missed the previous webinars, you can find them on Biomass Canada website on the webinar section, and you can have access both to the presentation slide and also the recording of the webinars. By the way, I forgot to actually introduce my name. My name is Mahmoud Avadian. I'm a research associate at the University of British Columbia. I work with Biomass and Bioenergy Research Group, as well as Forest Biotechnology and Bioenergy Research Group, working on biomass, logistics, and supply chain analysis and optimization. So let me just give you just a quick background on Biomass Canada Cluster. So this is a cluster established in 2018, and it's led by Biofuel Canada Network and with the financial support from Agriculture and Agri-Foods Canada's Agri-Science Program, as well as the contribution from industrial partners. As I mentioned, that we have 10 activities or 10 projects, and each of them, they tackle different aspects of the agriculture biomass value chain, from production of biomass to logistics and supply chain, and also pre-processing and pre-treatment and conversion of the agricultural biomass into the final product. So the focus again is on enhancing the contribution of the Canadian agriculture into the growing Canadian bioeconomy. So that's been the main focus of the Biomass Canada cluster. And today, Dr. Dalai is going to actually talk about 2 activities. One of them is focusing on the production of biochar, more as a high-value product for soil amendment, for example. That's one of the applications. And also, he's going to talk about some of the pre-processing and pre-treatment technology he has been working on. So just a quick introduction of Dr. Ajay Dalai. I'm sure you know he's one of the leaders in this space. So I'm sure most of you already know Dr. Ajay Dalai. He's a distinguished professor and Canada Research Chair at the Chemical and Biological Engineering at the University of Saskatchewan. And again, as I mentioned before, he's been leading the activity number 4, which is mainly focusing on the production of biochar, and also activity number 9, which is on the application of thermochemical and hydrothermal pretreatments in production of fuel pellets using agricultural waste. So before I hand it over to you, Ajay, just let you know that we are going to, similar to the previous webinar, we are going to record this webinar, and then we post a copy of this recording and also the presentation slide after this presentation, and you can have access to this one after the meeting. And if you have any question, please make sure that you put all of your questions in the Q&A box. And then after each presentation, we try to address as many questions that we can based on the time we have. Okay, so with that, I hand it over to you, Ajay, and we're looking forward to your presentation.
Okay, thank you, Mahmoud, for kind introduction, and good morning to you all. And again, thank you those who are going to listen for next 45 minutes or so. I hope it will be a good interactive session, and hopefully learn from one another. And again, thank you for your time. So let me share my screen and then start my presentation. So this is my screen here. Can you see this?
Sounds good. Yes.
Okay. Again, Mahmoud, thank you again. Saumin, I see you attending this as well. Thanks to you for taking care of all the logistic, everything over the last 4 years or so. So today I'll be talking about two projects, as Mahmoud mentioned. One is the biochar, and the other one is biopellet for industrial applications. And we are focusing more on the agricultural biomass, as we have been funded by industry as well as by the Agriculture Agri-Food Canada, as Mahmoud mentioned. So let me first talk about activity 4. This activity deals with the biochar production.
Ajay, do you mind to go to the full screen, please?
So it's not full screen?
Not yet, no.
Oh, I'm sorry. Okay, yeah, absolutely. Yeah, thank you. Is it better?
Yes,
Yeah,
thanks.
thank you so much. So the goal of the activity 4, as Mahmoud mentioned, is to deal with the biochar production from Canadian lignocellulosic biomass and applications for carbon sequestration, soil improvement, and crop productivity. So in this particular project, we have basically 3 focus. One is to look at the pyrolysis and gasification of local Canadian agricultural biomass. And those include the canola meal, canola hull, oat hull, canola hull as well, and then the mustard meal, etc. And we're looking at to produce biofuel and syngas, and for soil conditioning as well. So the application that we looked at is on soil fertility, crop productivity, environmental absorption, pollutants, including CO2 capture. So the idea here is to take the agricultural residue and advance the utilization of biochar as an inexpensive source for carbon and nutrients for improved plant growth, soil restoration, and carbon capturing. So just to give a very brief introduction, if you look at this particular slide, you'll see that it's a global warming happening due to the and leading to temperature rise, and that also is the due to the accumulation of CO2 in the environment. And the CO2 accumulation is more prominent over the last 30-40 years due to more industrialization, more usage of energy, and also for better quality of life. And then this CO2, about 80% of the CO2 is coming from the burning the fossil fuel. So when you look at the Canada's government of Canada's commitment to sustainability, we have a Kyoto Protocol that none of the countries were able to meet that protocol. And then we had a Paris Accord in 2015. And according to Paris Accord, we are supposed to reduce the greenhouse gas emission by 30% below 2005 level by 2030. And that is the goal. We have only a few years away. And also the developed countries are committed to more than $100 billion a year up to 2025 to help other countries to deal with the climate change. And because of the COP26 in 2021, most of the developed countries renewed their interest in helping third world countries by funding the projects to enhance the reduction of carbon dioxide to environment. And Canada ourselves, we committed to enhance target of reducing emission by 40 to 50% from 2000 level by 2030 as well. So Canada targets to achieve net zero emission by 2050. And so a lot of things we have to do to meet this particular target. So biomass is a renewable material, as all of us know. And if you can, we also know how biomass is grown through photosynthesis, taking the carbon dioxide from environment and putting that in terms of solid carbon in plants. And so that's how the carbon can be reduced. At the same time, if we can utilize the biomass for energy and soil amendment purposes and global environment purposes, I think it will be a win-win situation. So this slide gives the agricultural residue, forest residue and energy crop both in US and Canada. And you can see that we have a lot of this material available for utilization. So this agricultural residue that we're going to talk about more are mostly from the local grown industry. And the forestry sector has really done well in the sense that they have captured a lot of export market, like our food market, export market as well. But when you look at the bio residue from forest sector, they export about $400 million worth of pallets where agricultural residue, we have not been able to monetize that on that particular product. The energy crop is also largely available as well. And of course, they can be utilized as well to meet the energy demand as well as the climate change demand as well. So let me talk a little bit about the food waste. When you look at the Saskatchewan, we have about 48% of the agricultural land, and we produce a lot of oat and canola, for example. When you look at the food waste, about 1 kilogram of food and food product are wasted per person in North America, and that's per day. In North America, we have about 7% world population consuming about 20% of the food, and a lot of this food gets wasted as well. So the idea is to, if you look at this this diagram below, a lot of this food waste, agricultural produce, they go to landfills, and they support or enhances the breeding of pests, flies, microorganisms, and also they produce methane through microbial action. And methane has 21 times more greenhouse gas effect than carbon dioxide itself. And if you look at the greenhouse gas emission in Canada, we are at 730 million tons per year, and that's quite substantial. And that number is actually going up instead of going down. So when you look at the agricultural material, we are looking at thermochemical conversion for biomass, and that includes combustion. A lot of third world countries, they burn biomass for cooking, for example, and gasification is another technology to produce the high quality syngas, which is a mixture of hydrogen and carbon monoxide, and that's a building block for fuels and chemicals. And the third one is the hydrothermal liquefaction, where we can get the biocrude oil and also produce some gas and biochar. So the pyrolysis, as all of us are familiar with this particular process, this is a process leading to bio-oil, biochar, and biogas production. And then this carbonization torrefaction technology basically leads to the production of more solids than the liquid and gas. So as I mentioned, the pyrolysis is one of the processes that have potential in converting biomass to useful products, and it's an endothermic reaction, and it happens without the presence of oxygen or air. So when we do the pyrolysis, it degrades the solid organic material to mostly biochar, bio-oil, and also produce some non-condensable gases such as synthesis gas, methane, and carbon dioxide. And the biochar can certainly be converted to activated carbon for better use because of its better physical and chemical properties as compared to the biochar itself. So when you look at the three kinds of pyrolysis process, slow, intermediate, and fast, it depends on the how fast or how slow we heat the reactor for this process. For example, for slow pyrolysis, we need more than the vapor residence time is more than 30 minutes compared to fast pyrolysis, which is less than 2 seconds. So the physical process conditions for physical, and there are two kinds of activation process for making activated carbon from biochar, for example. Those are physical and chemical activation. In case of physical activation, steam, carbon dioxide, and air are used, whereas in chemical activation, some of the alkali elements are used. So this particular page shows the temperature range, activation time range, surface area that we can generate, total pore volume that we can generate, and average pore size that we can generate through physical and chemical activation processes. So once we look at the biochar, this biochar has a lot of applications, as you see in this particular page. When we increase the temperature from 300 to 700 degrees C for biochar production, the aromatic content, the ash content, the pH, surface area, pore volume increases. And when we decrease the temperature at lower temperature, we get higher yield, higher yield, and it's more conducting, and it also has better cation exchange capacity. So the biochar itself, you can see, has a fuel application, agronomy application, carbon credit application, specialty materials, including biocomposites and fuel cell photovoltaics. And also it has some biomedical use for pharmaceutical and gas storage. And then it can also be used for catalyst support, adsorbent, water treatment, etc. Of course, it has also a fuel application due to its high energy value for gasification, coal firing, combustion, etc. So if you look at the graphical representation of the activity 4 that we are doing, so for example, we are taking the oat hull and canola hull and food waste and producing the biochar through, say, pyrolysis process, and then take that biochar and activate with the potassium hydroxide and steam, for example, through chemical and physical activation in this temperature is 7 to 900 degrees Celsius, and activation time 60 to 120 minutes to produce. And then we go through a experimental design to optimize the condition to get high quality product in terms of porosity, surface area, yield, etc. And then this activated carbon we apply for one example here is the dye adsorption. You can see how we are able to remove a lot of dyes from the activated carbon. So shows the photo before and after. And we have been working with Professor Shanu in College of Agriculture here on the soil amendment, and we are doing on our own on the CO2 capture process. So this is a schematic of a fixed bed reactor, pyrolyzer reactor, where we have basically a tube encased in a furnace for temperature control, and we have also mass flow controller to monitor or control the flow of nitrogen into the reactor during pyrolysis process. And this process, of course, gives some condensed liquid and also gives some gas that we analyze on a continuous basis. And also we can capture the solid in the reactor after cooling the reactor with nitrogen. And you can see the temperature, heating rate, reaction time, nitrogen flow, etc. are basically optimized for getting a high quality product. So this particular page shows the ultimate analysis of biochar, biomass and biochar. when you get any residue, for example, food waste, canola hull, and oat hull, we'll do the ultimate analysis and also the calorific value. And here you can see the carbon content and the oxygen content are very, very similar. And the higher heating value is a little bit lower range in 17 megajoules per kilogram. And it's much, much less than that of the coal, for example, or natural gas. And when we produce the biochar at different temperatures, this is the food waste we are talking about, and then this is the canola hull and oat hull. So at different temperatures, when we do this pyrolysis, we found that at 600 degrees C and for 1 hour, so the material has a very little oxygen content, as you see, gone down to 2.5 from 40% average. And the heating value has increased from 17 to 23 megajoules per kilogram, which is very ideal for using even for biocoal. And the pH is more alkaline in nature. And at this same condition, we look at the canola hull and oat hull, and it gave a little bit more oxygen content, and the calorific value is a bit higher, and the pH in the same ballpark range. But the most important thing, the carbon content of this material is increased by eliminating the moisture and volatiles from this material, and degrading some of the cellulose, hemicellulose, to create some of the lighter components that leave the material to make it carbon rich, for example. So this one shows the pyrolysis, more detailed pyrolysis product from food waste, and we see that the distribution between biochar, biofuel, and gas. So it's roughly about 30, 30, 28, 32, 30 in the same ballpark for the temperature 600 degrees C 1 hour and heating rate of 5 cc per degrees C per minute. And we also looked at optimizing the heating rate as well. So in this particular page, we see the optimization of temperature, reaction time, and heating rate to get a high quality product from the food waste in terms of biochar production. So what we did is looked at the scanning electron micrographs of this material. So this is the top left is the food waste biomass, and then you look at the food waste biochar produced at 300 degrees C for half a minute, half an hour. And the bottom left is the one that is created at 600 degrees C for half an hour. And the bottom one, you can see it's more complex, more a little bit porous as compared to the food waste raw biomass. And when you look at the thermogravimetric analysis, we find that the cellulose and hemicellulose decompose rapidly for the waste food waste, for example. And when we subjected to the higher temperature for biochar production, the thermal stability bit higher, which is a good sign. And when you look at the NMR, solid state NMR, on the distribution of aliphatic, aromatic, and acidic material present in this. So the food waste has had more aliphatic material, and we subjected to higher temperature. Then the aliphatic and then the aromatic component went down. Acid component went down, and then you get more aromatic structure. That is kind of visually reflected in the bottom left ACM micrograph. So then after looking at the extensive production and activation, production and characterization of biochar, we looked at the activation. So this is a pilot activation process, or the pilot scale reactor that we have in the lab, where you have a boiler and a superheater. And here is a reactor which can take about 5 kilograms of material for activation purposes. So this particular slide shows the impact of activating agents, say potassium hydroxide versus steam, in the temperature range of 700 to 900 degrees Celsius. Activation time between 1 hour to 3 hours, 1 hour to 2 hours. and then and their impact on the specific surface area, total pore volume, activation size, and the yield. So we found that when you activate with the steam, the surface area is relatively low as compared to the surface area we find with the potassium hydroxide activation process. And then the yield is also a bit low in potassium hydroxide case, which is more reactive more reactive during activation process than what the steam can do. So here is the interactive effects plot between activating agent, agent temperature, and activation time. So you see that the mean surface area, how drastically is increased by about more than threefold when you change from steam to potassium hydroxide. And the temperature impact is also there. So we can see that how the surface area goes up with the increase in activation temperature, and then activation time has a more or less smaller effect than the other two. So this interactive effect shows that the activating agent has more impact compared to temperature, and temperature has a more impact compared to activation time on the surface area of the material. So if you look at some of the data at the bottom, we see the canal hull, wort hull, the surface area in the ballpark of 550 to 730 square meter per gram. And the yield is about 47 to 49%. And the yield is very, very important when you want to really make money on selling this the activated product or the activated carbon. So the yield basically gives the revenue. So I think yield is a very important factor. And when you look at the chemical activation process, the same feedstock gave about threefold or 2 to 3-fold higher surface area. And the total pore volume is larger. So in the layman's term, the pore volume is the one that retains it's helpful to retain the moisture, etc., and for longer time within the soil. So the pore volume is important, and this higher surface area is better to retain some of this material that goes in the soil as well. So the average pore diameter in the same ballpark in both the cases is about 3 nanometer on the size that these products have. And yield is again in the same ballpark as in the case of the steam activation process. So again, just try to choose only few results. Don't want to show everything. So here you can see that we have two diagrams. One is the methylene blue removal process, which using the steam activation process and potassium hydroxide activation process. And we find that the wort hull, cannula hull, etc., have a low absorption capacity for this dye. And the wort hull is a little bit better. You can see the commercial product does a little bit better than the biochar itself. But when we activated the steam for this wort hull and food waste and cannula hull, we find that the absorption capacity went from say almost 0 to 60%. Whereas in case of potassium hydroxide activation process, you can see that in food waste and also food waste, how it has gone to close to 100, for example. So let me switch to the carbon capture work. So when we burn any fuel, we produce carbon dioxide and methane, NOx, SOx, some of the mercury, depending on what this material has. So it really pollutes the environment, and it also it gives about and of course that's a function of the temperature, etc., for the combustion process. So when you look at the post-combustion carbon capture, the key technology is required to achieve net zero soot emission is carbon capture and storage. And adsorption on activated carbon is one of the potential methods. I just talked a little bit briefly on the activation process. So it requires a low energy content for for the adsorption, or it could be cost effective, and it can be applicable in a wide range of temperatures and pressures. So what we have done is this slide shows the CO2 adsorption results of selected activated carbon products. And here is the impact of temperature and concentration of carbon dioxide in the feed gas. So we find that if you are the similar condition, we decrease the temperature, say 65 to 25 degrees C, almost with the 30% CO2 concentration in the gas. The potassium derived activated carbon it's adsorbs more, so it gives about 78 grams per kilogram of adsorbent, as compared to the carbon dioxide treated activated carbon 63 compared to steam. It's 59 grams per kilograms of adsorbent or the activated carbon. So we know that the adsorption process is endothermic. I'm sorry, exothermic. So lower temperature works better, as you see in this particular table. So we reduced the temperature to about 17 degrees Celsius, and we found that the impact of the temperature on the adsorption efficiency is not drastically different as compared to the one at room temperature. So this one gives the interactive plot for steam activated carbon and potassium activated carbon for the CO2 adsorption capacity in terms of temperature and CO2 concentration in the gas. And we find that when you increase the temperature, the adsorption capacity goes down to some extent, and also goes down to goes down to some extent, and some from 25 to 65 degrees Celsius. And when we increase the CO2 concentration 10 to 30% in the gas, it has a better impact on the adsorption efficiency. So we also looked at the role of biochar in soil improvement. Many of you are very familiar that the biochar may contain the nitrogen, phosphorus, and potassium that can help to supply essential nutrients to plant roots. And it basically forms a complex with the soil and plant roots to prevent soil erosion. And it can also retain water, for example, to keep the soil moist, as this surface area and the porosity that we discussed provides that that opportunity for the soil to retain, or the biochar to retain the water. And there are many other properties that can enhance the texture, fertility, water content, salinity, nutrient, and organic matter. And also biochar holds the stable carbon in the soil, helping in carbon capture and sequestration. And it can also increase the crop productivity, and it can hold beneficial bacteria and fungi within its porous structure to continually supply plant growth hormones and aid in carbon and nitrogen fixation. So we have done some work in that area. That work is continuing, and this is the last year for the project. So we are working with the soil science department to get some results on this. So we find that when you look at the food waste biochar produced by slow pyrolysis, we find the optimum condition to get a better product. And also we found that the oil that is produced from food waste has a highest carbon over 67%, hydrogen over 9%, nitrogen over 6%, and heating value over 32 megajoules per kg. And I did not present the results on bio-oil, but just wanted to let you know that we have extensively worked on the bio-oil analysis as well. And this material has a higher heating value, so it is also a good sign. And when we activate this material, we found that the activating agent has a better impact than the temperature and activation time to get a better product. And we also looked at the methylene blue, methylene violet, and the rhodamine B dye adsorption using the potassium hydroxide activated food waste. And we found that, and also for the canola hull as well, and they are very, very effective. So let me go to activity 9, then we can maybe have some discussion at that point. So
So Ajay, if you don't mind, let's see if you have any question. That would be a good break, at least for you and also for the participant, if you are okay.
yeah, it's fine. We are just halfway through, so I'll be fine. Yeah.
Yeah. So I can actually start with the question and then see if participants they have any other questions. So Ajay, you talk about bio oil and some of the quality of the bio oil. Have you done any comparison between the bio oil from agricultural biomass with the bio oil from woody biomass in terms of the quality, especially for transportation biofuel production?
Absolutely, that's a really good question. And you find that the bio oil from the agricultural residue in terms of, let me go back here, in terms of the carbon content, hydrogen, nitrogen, etc. It has a better value as compared to the oil from the forest sector. And we have also done some upgrading of this oil by adding hydrogen or removing water to get a better product for transportation sector. So we have been working on this area. That's really good question, and we are working in this area to maybe get more meaningful result in terms of comparison, as you mentioned, Mahmoud.
Okay, thanks. So two more questions, Ajay. The first one is, what do you think as the main barriers preventing the application of pyrolysis of agriculture based on larger scale in Canada?
That's a good point. I think the greatest barrier is the cost of transportation, and I think the second part of the work that I'm going to present adds value to this question. So when you look at the agricultural biomass, there are seasonally there is a lot of variables there, quality, quantity, etc. So the supply chain is quite challenging. And then the other thing is to transportation cost, and then the pre-processing cost for the biomass for the pyrolysis process. So there are some front-end cost, and also to get the bio-oil and find a stakeholder to take and utilize the bio-oil. It's also there is a it's not a really clear path there. So I think these are the reasons why this has not been very popular. And this is part of the work that BiofuelNet is trying to do to address that bottleneck and remove those challenges and bring some of this technology to the industry so that they can think about scaling up and making money on this process.
Yeah. So just follow up with this question, Ajay. You mentioned that one of the barriers is pre-processing of agricultural biomass. So for your process, for your technology that you have been trying to develop, in order to produce bio oil from agricultural biomass, what are those? So I'm sure you do grinding, you make sure that the moisture content has a specific level. Can you talk a bit about those pre-processing you have done, before you feed it into the reactor?
Absolutely. I think the pyrolysis process is an energy intensive process, and it's endothermic process. We have to supply a lot of energy. So in order, before we do that, we, as you mentioned, Mahmoud, in the pre-processing, we just have to make sure that we don't have any moisture in the sample, in the feedstock, so that costs money. The drying it's not cheap. Plus, we have to grind it to certain particle size so that it can undergo that transformation in the reactor in a short time to get more oil. So the grinding is also not cheap. So those are the things. And before that, of course, you have to transport, as I mentioned earlier, from the production site to the processing site. So that's just a lot of cost involved there as well. But once you get the oil has a very high calorific value. Transportation is easy. We have also found ways to remove the water from the oil, so that it's not that difficult. But once you get the water out, it becomes very dense and very viscous. So the biochar, the bio oil that is produced is also not very stable under environment and the atmospheric conditions. So we have looked at the stability of the bio oil, how long it can be retain its property at room temperature when exposed to air. So we have done a lot of work in that area as well. And then I think it has to be blended with maybe alcohol, ethanol, for example, for the further processing and upgrading. So this oil is not only good for burning, but also we can reform to produce hydrogen, for example, or syngas by reacting with the steam. And also some of the phenolic compounds can be fractionated out of this bio-oil as well. So I think the idea is to take some of the valuable components out of the oil and then take the rest and burn it or produce hydrogen, for example, through reforming reaction.
Okay, thanks. And the last question before go to the next presentation, Ajay, is that can you comment on the impact of the ash content in the feedstock on the properties of the biochar and activated carbon?
Absolutely, absolutely. I think that's a really, really good question. So whatever ash we have in the feedstock is retained in the biochar. So, for example, if the biochar yield is say 50%, and then the feedstock has say 5% ash, so that becomes 10% in the biochar because that's retained there. The yield is half, therefore the ash content is doubled. And that biochar, when you activate it to say 50% goes to say 30%, then the ash content is also increased in the biochar. So that is an issue. And what we have been doing is look at the quality of the ash and see is it compatible with the soil. Do we have to use some of the chemicals to take the ash out from this material, and what stage, either from the feedstock or the char or the activated carbon. So what stage we can take this ash out, for example. So I think it's a challenging area and it requires some attention, and we have done some work in that area, as I mentioned.
Okay, great. Thank you very much. I guess we are good for the second presentation. Thanks, Ajay.
Yeah, thank you. And thanks for great questions, Mahmood, and all the participants. So the second part is looking at the thermochemical and hydrothermal pretreatment in production of fuel pellets using agricultural materials. And when you look at the production of pellets, we are looking at the torrefied biomass through and also hydrochar as well. So we are using this torrefied biomass and hydrochar. Hydrochar is a product that when you look at the wet biomass, for example, we discussed on removing the water for pyrolysis, and removing water is expensive. So the hydrothermal process is a process where we retain the moisture in the feedstock and then treat it at higher temperature and pressure to get some liquid and then get some char and get some gas. So the hydrochar is a product from the hydrothermal process for biomass. So we get basically two kind of product. One is torrefied biomass and the other one is hydrochar. And we have been working on the production of fuel product from these two sources. And of course, they're all related to the agricultural residue. We're looking, we have optimized the biomass pellet gasification process as well, and working on the scaling up and piloting of new pellet agent gasification process. So like Sahab in UBC has got the pelletizer from Sweden. We have the same unit here. So we have not really located that unit in any industry yet, but we have some thoughts. We have been talking to Sahab as well. There are some local industry interested to take it and produce the high quality pellet with our recipe in a little bit larger scale. And we are working on the life cycle and techno-economic analysis of this biomass pre-treatment pellet production and gasification process as well. So those who are not familiar with this pellet export market, I mentioned very briefly in the beginning. So you can see how the pellet production and export market is going both for Canada and the United States over years, of last 10 years or so. Again, please look at the global ranking and export market for wood pellet in 2017. So here is the United States percent of world value is 26%. Canada is not behind, it's about 12%. So I think you can see the provinces, different provinces that are exporting fuel pellets to different countries. And the amount are here, so you add them up, is close to $400 million. And these are all from the forest sector. So the idea is to make the recipe for the agricultural industry to prepare pellet and export to other countries as well. So our approach has been to use the canola hull, oat hull, canola meal, and barley straw, and also we have used the mustard meal as well. And so we, as I mentioned, we are doing the hydrothermal and the torrefaction pre-treatment, and then co-pelletize them with the original precursor. And then in cases if you have not torrefied before, we are just using hydrothermal pre-treatment. For example, we are torrefying the product as well. So those who are torrefied would compare that product with the torrefied after, for example, and then look at the steam and hydrothermal gasification to produce the biooil gas and biochar from this product. And these basically two activities are intertwined in the sense that we want to produce the biopellet right at the source and then transport the material to more the pyrolysis or gasification sites. So those who are not familiar with the torrefaction technology, it takes place between 200, 300 degrees C with reaction time between 10 and 60 minutes in inert atmosphere. And it leads to the condensable liquid and non-condensable gases. So when you look at the biomass and the torrefied product, to compare them, the parameters are here. So the biomass has high moisture content, torrefied has a low moisture, and biomass has a low calorific value, torrefied biomass has high calorific value, and the biomass is hygroscopic, here is hydrophobic, and it has a poor grindability, and it has a better torrefied biomass with better grindability. And biomass has a high volatile content, and the torrefied biomass has low volatile content. Biomass has a higher volume, torrefied biomass has less volume. Biomass has low bulk density, and the torrefied biomass has a high bulk density. And biomass is non-uniform properties, and torrefied biomass has more or less more uniform properties. So you can see, and so this is a review paper we published in 2020, where you look at the comparison of the biomass before and after torrefaction process. And we are convinced that torrefaction process is a very useful technology for getting a better product from biomass. And when you really treat it at between 200 and 300 degrees C, we are removing the moisture and also volatiles, etc. And also we are doing some undergo some reactions as well. So here is the biomass torrefaction. You get torrefied biomass. You can see it has many applications. One is the densification. We can do gasification, we can do pyrolysis, we can do combustion, and do co-pyrolysis, and also for metallurgical applications as well. So when you look at the effect of temperature on torrefaction of lignocellulosic biomass going from 200 to 300 degrees C, and we know that lignocellulosic biomass has a lignin, hemicellulose, and the cellulose. You can see what happens to all these components as the temperature increase from 200 to 300 degrees C under inert atmosphere. And so as we move from the lower temperature to high temperature, we have more degradation and cleavage, etc. happening to some of these molecules, leading to a better product. So now let me switch for the hydrochar production. I briefly mentioned. So we have a autoclave, 1.8 liter autoclave. So you can load up to say 1 kg or 1 liter of the 1 liter of the material. And the temperature it's a subcritical condition, 210 to 270. Pressure is it's autogenic pressure, about 2000 psi. And biomass is about 15%, and the rest 15% in 15 to 100 in mass basis biomass to water. reaction time is about 90 minutes, and then we have some spinning or the rotation in the so to have create a homogeneous mixture. And the other one is the torrefaction. We use a bench scale microwave hot air oven, and you can see the operating condition, the temperature range. It's about the power range 350 to 450 watt under nitrogen environment, and the reaction time is maintained at about 20 minutes. So when you look at the once you create the biochar, for example, from the canola mill, oat hull, and canola hull, we have a bench scale extruder. So where we basically manipulate the ratio of biomass to water and the hydrochar to canola meal, and push it through a die at hot condition to create the high quality pellet. So on this one, look at the effects of biomass to water mass ratio for the hydrochar, for example, from the canola hull, oat hull, canola meal, and here is the canola meal is so this is the canola meal hydrochar, and then you can see the so this is the oat hull hydrochar, canola hull hydrochar, and here is the CM is the canola meal. So we have different amounts of biomass to water ratio, and look at the relaxed density, which is the density measured after 2 weeks of storage. And we find that when hydrogen to canola meal ratio is about 50-50, and in all cases the ratio is about 50-50, and we find that you have a little bit higher biomass to water ratio gives a little bit higher relaxed density in the final product. We also looked at the characterization of the co-pelletized hydrochar with canola meal. So again, we varied the ratio of the hydrochar to canola meal to measure the relaxed density and mechanical durability. And we find that in all cases, the biomass to water mass ratio was in the formulation was 2.5, and the relaxed density as I mentioned, measured after 2 weeks of storage. So we find that when you increase the canola meal content, the relaxed density or the mechanical strength increased, and then the relaxed density decreased to some extent. We also looked at optimizing the biomass to water mass ratio for the canola hull. As you see, the ratio varied from 1.5 to 3. And we will find that when the ratio is about 2.5, the density is about 1000 kg per cubic meter. And the impact resistance is really, really good. Breaking force is very high. And the higher heating value is about 19 megajoules per kg. And then the moisture uptake was a little bit lower as in other cases as well. You see in this table. So we also co-pelletize torrefied biomass and look at the relaxed density, durability, breaking force, higher heating value, and moisture uptake. So we find that when we so this TCH is the torrefied canola hull and torrefied oat hull here. And when we vary the ratio, for example, in the range of say 25-75 to 75-25, we find that somewhere in the middle it gives a little bit better product. We also did the synchron-based studies on these pellets, where you can see, look at the porosity on the top view as well as the side view. And we find that in some cases the porosity as you see varied from about 8 to 15%, and the blue color here reflects the porosity in the material, internal porosity of the material. So this is a very powerful tool to look at how the material, the pores are more or less uniform, or they are non-homogeneous, for example. And we find that the void space of the porosity is directly related to the pellet mechanical strength, as you would imagine. Higher is the porosity, lower is the mechanical strength. porosity also affects the hard hitting value, the combustion property, self-ignition property, moisture adsorption property, and the microbial attraction as well. So the measurement of this internal porous structure and looking at its uniform nature or non-uniform nature becomes very important, especially for export market. We also looked at the effect of torrefaction on water resistance of pellet when we varied the canola hull, wort hull, torrefied canola hull, torrefied wort hull to the mustard meal ratio, and it shows the moisture absorption capacity as well. So in some cases, you can say the equilibrium moisture content before water immersion is about, it varies from 9 to about 20% now with these different materials. So what we find is the equilibrium moisture content of pellet decrease after torrefaction due to the removal of free water, light volatile, and degradation of hemicellulose content during torrefaction. And we also find that the free water present in the biomass or pellet is directly related to moisture absorption. A rise in relative humidity results in increase in free water in biomass. So we also looked at the pellet application for pyrolysis and mostly for pyrolysis and also for gasification purposes. Also, as I mentioned earlier, we can use for combustion, cooking, burning, heating. We have one of our partners set up here with Hehe Holding in Montreal or Ottawa area. So which basically we can do the combustion and look at the emission from this pellet during combustion process. We have not really started that. It's difficult to do the combustion in a lab, especially within the lab environment, but we have the unit there that we intend to take it out to some industry to do some of the combustion tests to look at the pollutants coming out of these pellets. So with that, let me conclude on this part. So we find that the biomass to water ratio can be 2.5 to provide highest breaking force, impact resistance, and density of canola hull pellet. And we also find that increase in hydrochar concentration on pellet formulation reduce the pellet density as well as durability. We also find that the increase in torrefaction temperature and time enhance the energy content by 31% per canola hull. We also find that the optimum pellet formulation of a torrefied pellet is 50-50, especially for the torrefied canola hull or torrefied wort hull to mustard meal ratio. And we find that the mustard meal has some oil that helps in the lubricating during the pellet formulation, also provide hydrophobicity for the pellet. And we also measure the density, relaxed density, durability, tensile strength, and high heating value of pellets, which we believe are important properties of the pellet for large-scale production or for internal or external use by industry. And we also find that if we put too much mustard meal, then it increases the heating value, but also increases the moisture uptake rate of the fuel pellet. Too much of that is not good. So the critical success factor, I think this is an important slide. So to improve the pellet property, the use of treatment instead of additives decreases the final cost of produced fuel pellet. So that's what we are trying to focus on. And the low price fuel pellet would be a strong candidate to replace cheap coal in the fuel market. And this material can be, because they're coal-like material, they can be easily co-fired with coal in power plants. So I think the SAS Power at this point is doing a feasibility study to bring in fuel pellets to the Boundary Dam power plant, which is based on coal to complement their operation. So the feasibility study is going on. The production of high quality fuel pellet from low value agricultural residue can have a strong market for export to other countries and can attract and benefit farmers and the country in general. So in addition to the biofuel net, we have New Life, Provita, and also Hey Hey Holding, SAS Canola. So all these different biofuel net, of course, Agriculture, Agri-Food Canada, Western Economic Diversification, which gave us about 1.4 million to buy all the equipment we need for our research. Canadian Light Source, we have been working on the fuel pellet quality and the structural science center on campus, which is about $17 million worth of equipment, including NMR, X-ray, photoelectron spectrometer, etc., to characterize XRD, to characterize our materials. And there are some of them are very useful for AS quality measurement as well. So these are some of the collaborators from the UAPS that we have. We have Martin Rennie, that some of you, unknown caller, some of you may be familiar with, and also others in the department and outside department as well. So we have a Dr. Moshiri from economics, who's helping us the techno-economic analysis. We have published a paper recently, and it's very resourceful. And part of this, we are going to work with PAMI as well, which is a provincial center on this techno-economic analysis as well in this year, with some funding from the Ministry of Agriculture within the province. So some of our collaborators over the years also have done some work with Don in McGill, and of course with Franco from Western, and we're familiar with a few other people, Janos, which is Dean of Lakehead right now. So we have some collaborators within the country and outside the country on this and other projects. So this is the research team in the lab. So about half of this group works in the biofuel net project, those two activities that I mentioned. Again, thank you for your attention, and we may have some time to discuss as well, and Mahmood can coordinate that as well. So thank you so much for your attention, and I hope it was a little bit useful. And we are here, you are there, so you can also have other opportunities to discuss as well. Thank you so much, and have a nice afternoon, and have a nice long weekend ahead.
Thank you very much, Jay. Great presentation, and I see that you have a really large research group. So lots of hard working is happening in your research group. So
yeah. So as you can see, they're very colorful. We have a lot of students from Iran and India and Bangladesh and Nigeria and Ghana, China, some of our own students from here as well, some Mexico and Far East. So we've got a combination of people from different places.
Oh, this is great. Thanks a lot. Yeah. So I have two questions, and see if we get some other question from a participant. So AJ, you mentioned about you have been using mustard meal and also canola meal in your application. I'm just curious that this is my understanding. Maybe I'm completely wrong. That, like, for canola meal, there is some nitrogen in the canola meal, and if you use, so if you produce any type of pellet for bioenergy application, that nitrogen could be a challenge when you burn it in a combustion chamber. So what's your thought on that? And if there is any nitrogen, how we can actually remove that from canola meal?
Actually, that's a really good question. I have to go back to the lab and think a little bit about in that way. As I mentioned, that our combustion unit we have not really fired it up, and that's where we want to look at some of the emission coming from this combustion or gasification of these pellets. So we have done some work with the combination of coal and Ramin, who is a faculty in St. John's. He did some work on the coal and bio pellet combination. And there's a lot of synergy there. The coal has a lot of pollutants, biomass is a bit cleaner. And when you combine it, so hopefully the nitrogen balance can be balanced in the environment. So I think that is, and we also found that biomass has more hydrogen than the coal. Coal has more carbon than biomass. So there's a synergy to produce high quality syngas from this material at the same time to balance the nitrogen emitted to environment.
Okay, thanks. And one question from the participant, how much energy is required to produce the hydrochar as a fraction of the total energy content in the finished hydrochar?
Absolutely. I think that's really, again, a good question. So the energy consumption, when you look at the hydrochar production, as I mentioned, it's a subcritical water treatment, and it consumes a lot of energy. And so the idea is to get the energy from 2 or 3 sources. One is the get the energy from the nuclear industry. For example, Saskatchewan is looking at investing in nuclear power plant. So some of the energy may be available to utilize for bioenergy, processing, bioenergy products. The second one could be from solar, for example. Solar and biomass can be integrated to get that energy from the solar sector. And the third one is part of the biomass can be also utilized on site by burning, or as we discussed about bioil, burning bioil to provide the heat that we need to do this kind of treatment to produce hydrochar.
Okay.
So there are different ways we can do, but that's a little bit down the road.
Okay, thanks. And my last question, Ajay, you mentioned that the torrefied pellet has a cold-like properties. So my question is that have you tried to like leave it outside, like exposed to the element to see how that's going to react with if there is any rain or like moisture outside, so whether it's going to disintegrate or not?
Yeah, that's again a good question. I think you and Saab and like in your lab, we have done a lot of work in leaving the torrefied biomass derived biochar in more moist environment, and I think it does well as compared to the biopellet produced without torrefaction process. So our experience has been the torrefaction of the biochar leading to the production of the biopellet is a better way to repel moisture during storage and transportation.
Okay, great. Thank you very much. Great presentation. And as Ajay, you mentioned that in order to increase the uptake of special agriculture biomass, we definitely need commercialized pre-treatment and pre-processing. So a lot of work is happening in Biomass Canada cluster, and we are going to actually continue this type of project for the next cycle. So thanks again a lot for all of the work you and your team has been doing at the University of Saskatchewan. And again, thanks to all of the participants, they join, and also for the great question. And I hope everyone has a safe and long weekend and happy Canada Day.
Yeah, and I see Sahab as well. I'm so glad that Sahab had some time to listen, and many other participants that I know, including Xiaomin and yourself. So it has been a great afternoon here in Saskatoon.
Great. Thank you very much. Take care.
Thank you. Thank you all, and have a good weekend.
Thank you. Bye.
Thank you. Bye.